All right, so in this video, we're going to talk about kinetic molecular theory. And what this theory is basically the underpinnings of the ideal gas law. So everything that this theory states is a rationalization for why an ideal gas is ideal and what the assumptions that are made uh, uh, give basis to this idea of an ideal gas. So if these assumptions are bad assumptions, i.e. they're not, very accurate under some conditions, that means that you have some gas that is non-ideal. And we'll talk about that a lot, okay? So the basic assumptions of kinetic molecular theory are as follows. First, gases are in constant motion. So they're constantly moving around. This is a very good assumption. Second, gas particles are not attracted to one another, okay? Now, this is an assumption that isn't always true, okay? And in fact, it's never completely true. All particles have some attractive forces between one another, okay? But this is particularly a bad approximation at high temperatures, okay? Or, at low temperatures. It's a good approximation at high temperatures. It's a bad approximation at low temperatures and high pressures, because at low temperatures, well, your gas molecules aren't moving as fast, right? Because your average kinetic energy, this is this fourth point here, is basically the speed related to the speed of which the gas molecules are moving is directly proportional to temperature. In fact, you can think of temperature as just being a measure of the average kinetic energy of molecules. In this case, we're talking about gas molecules, but it's true for any phase of matter. So yeah, at low temperatures, gas molecules aren't moving as fast, they're moving more slowly, more chance for there to be attractive interactions between those molecules or those particles as they collide. And same thing with high pressure. At high pressure, you have a greater density. You're squishing all these particles together. And so there's just more collisions. And so there's more chances for the particles to be attracted to one another. So that's when this assumption is a bad one. The volume of gas particles is negligible is the third assumption. This is, again, pretty good assumption because gas particles are not very dense, but as you increase the density, i.e. you go to higher pressure, this will become increasingly a worse assumption. We talked about how the average kinetic energy is proportional to temperature, and we're assuming all these things is another way of saying we're assuming elastic collisions, especially this gas particles are not attracted to one another. So what does elastic collision mean? It means you have billiard balls, for example, that bounce off each other at some speed, and they reflect and bounce off of each other at the same speed at which they're incoming. In other words, they don't lose any energy during the collision. And now we know this is impossible for any collision because, well, when those two billiard balls hit one another, sound is given off, so some of the energy must have been transmitted. Some of that kinetic energy that the billiard balls had before they hit was translated into sound, right? And also some heat is given off due to friction. And so when you take into account these things, that's called an inelastic collision. And so like a super inelastic collision would be something where the two balls hit each other and then just kind of stick to one another because there's so much energy given off during that collision. Okay. One thing here is you can use this equation. The average kinetic energy is equal to 3/2 times the ideal gas constant times the absolute temperature. So you can see this ideal gas constant is actually a kind of a fundamental property of temperature and energy. It relates these two things. So that's pretty cool. So more about kinetic energy and temperature here. There's something called the root mean square velocity. Essentially, this is very similar to the average speed, okay? It's a slightly different statistical analysis here, but very similar idea. And for practical purposes, you can think about it just as the average speed. Speed is just the magnitude of velocity. So not taking into account direction. So we can think about it as velocity or speed. But it's given by this symbol mu RMS, that stands for root mean squared. But again, it's like average. And formula is the square root of all of this expression, 3 times the ideal gas constant R times the absolute temperature. Again, your temperature has to be in Kelvin, divided by M, which is your molar mass. And I put this kind of scripted M, this fancy molar mass, because you have to use kilograms per mole. And the reason why you have to use kilograms per mole is because you have to use joule per mole Kelvin as R. So this isn't your normal 0.08206 liters atmospheres mole Kelvin that we use in PV equals nRT. It's the same value, just in different units that are more useful for us for solving these sorts of speed equations. It's 8.314 or 8.3145 joules per mole Kelvin. And so, we'll walk through an example here in a second to show you how these units cancel, but they do in fact cancel, and you end up getting the speed with these units in meters per second. Okay, and so here's kind of a plot of the distributions of speeds for a nitrogen molecule in this case at different temperatures. And you can see that as you increase the temperature, right, the peak speed here increases. So that makes sense. You're heating up the gas, giving it more kinetic energy, it can move faster, so greater temperature. All those things go together. And of course, if your absolute temperature is 0, which is impossible to achieve in practice, but in theory we can think about it, this average speed would be 0 as well. Okay, the molecules are stopped. All right, so this is the reason that helium, makes you sound like a chipmunk. It makes you have a very high voice. It's because basically the speed of sound through helium is much faster. So those helium molecules are moving faster. Why is that? That's because of this molar mass. So heavier molecules will move more slowly, right? Because this denominator will increase, this molar mass will increase, and lighter ones will move faster. All right, so now let's do this practice problem where we're asked, what is the average speed of an oxygen molecule at 25 degrees C? And so what we're going to do here is just plug it into our equation that we just went over, mu equals square root 3RT over the molar mass. And remembering that we have to use 8.314, the 8.314 version of the ideal gas constant. So joules per mole Kelvin, absolute temperature here. So we're in Kelvin. So that was 25 plus 273 equals 298. So converting from 25C into Kelvin. And then we have the molar mass of oxygen. If you look on the periodic table for oxygen, the atomic weight is 16. We have 2 of those oxygen atoms, so 16 times 2 is 32, so 32 grams per mole. But we got to divide by 1,000 to get it into kilograms. And why do we have to be into kilograms? Because a joule is a kilogram meter squared per second squared. And the way that works here is, or the way I like to remember that, because it's fairly complicated or just a lot of units. The way that I remember that is I know that I know this equation from physics. Kinetic energy equals 1/2 mv squared, and I know that the kind of SI unit of mass, or it is the kilogram. So the unit's going to be kilogram there, and then my velocity is going to be in meters per second. So I have meters per second squared, and so that's how I get this kilogram times, and I know my energy is joule, right? My energy is in joules. So a joule equals that, which is kilograms times meters squared per second squared. If you work through the units here, now everything cancels because this is actually kilograms meters squared per second squared, right? And what do we have here? Well, we have a kilogram on top on the numerator of this fraction, and we're dividing by kilograms, so those goes away, where grams went away here. And then we're dividing by moles here, but we're also dividing by moles there, so those go away. We're dividing by kilograms, dividing by Kelvin, but we multiplied by Kelvin, so that goes away. So we're left with just our unit analysis here is the square root of meters squared per second squared. And of course, we're taking the square root of both of those, so that becomes meters per second. And so the final answer here becomes 482 meters per second.